Welcome back. So in our second part of the lecture today, I'm going to show you some practical example that we produced using the computer simulation. Okay, so the software I will use is MATLAB. I don't know how many of you use MATLAB or ever used MATLAB, but if you have the UCSD account, you can access MATLAB free. Okay, the MATLAB usually is you need to pay for the software, but for UCSD students, you can get a free version here. I think UCSD MATLAB portal, so it will be free to download and free to use as long as your UCSD account is active. Okay, so if you want to try it out, I would say go ahead. So in our last lecture, we talked about the stream model, right? The standing wave and the stream model. And okay, let me find this thing. Yep, the stream model like this and like this. And we said we can use the digital waveguide like this, right? This structure to simulate the string displacement. But how does it work, and what's the how well it performs? So okay, so this is in Chinese, but let me do this. Okay. So this might be a little bit difficult to read, but let me briefly introduce this. This not really important. Let me just probably run this so you know what this program means. Okay. If I run this is the graph I will get, and you can see this is the initial condition. Okay, so the string. So this is our string. The string is sampled using 51 points, and this is the initial condition, initial position. Okay. So, which means for a flat string, now we are going to give this string an initial position here. Okay, a little bit. So this is still a plugged string. Okay, probably I should start with the plugged string model instead of this one. Yeah, to be more consistent with our teaching. So, okay, let me try this. So the struct model is here. Let me use plugged model first. Okay. So this will okay, so this is the model we just talked about in our last previous lecture. So this is the plugged string model, right? So this is the string, and we give this initial position like this. So we just pull the string here, and it will be like this. And after that, it will just propagate, right? Using two traveling waves. So this is our initial position of the string. And for the movement, we use the digital waveguide to simulate this. And here's the FFT is the frequencies. Okay, so before reading these graphs, okay, maybe you can give a listen. Okay, so the listen is just easy. It sound like this. You can hear my computer sound, right? I think. Okay. So this is the sound produced by this simulated string. So when we give it a initial position like this, and then we release the string here, and the string will vibrate. Okay, this will produce two traveling waves, and we will use the model. We'll use the model like this. We will have two delay lines, and we will add them together. Add the two delay lines together at some point and type it out. Okay, and then this is what we hear just now. So to read in this code, so this is the frequency. So we see the frequency is 440 hertz. Okay, so this is A4. The this is the A4. Okay, the note A4 is the frequency, and this is the sampling. Some parameter here gives you the filter actually. Okay, so this is the plug position. So we actually choose to plug this as 1/3 of the string, right? So we are plugging here. We're not plugging at the middle point. So this is 1/3 of the string length, and yeah, this is the initial position we're going to plug. And peak position, which means where we will hear, right? Because over the string, every place will vibrate. When we type it out, we need to choose one fixed position, right? One fixed position. For example, here we choose this position, and we only observe this the movement or the vibration of this position. Okay, so maybe this will move up first, and then down, then up, then down. So we only observe the position of this point, and we'll hear what this sounds like. And this produces the sound we just listened to. Okay. So we now use the plug string. Okay, so the plug string actually, so this is the initial position. We use this triangle. Okay, the triangle of this up and down of the form like this, right? This is up and down. So this is a triangle, and then we just code this initial position, and this is the delay line. So we have two delay lines as shown in this picture. We have two delay lines here, right? 1 and 2. So they encode left and traveling traveling waves. And n is equal to 5, so this is actually produced a sound of 5 seconds. Okay. And this is how we perform the computation using the delay line. And we are just, moving the points to the left or to the right, and we add a low pass filter here. Okay, so we are filtering the points, so it gives some natural damp to the sound, so it simulates, right, this absorption or friction of the material. And this, you can see this minus line, right? This minus sign is the reflection, because the string is of two fixed ends, right? The two ends are fixed. So when the wave reflects here, it will change the direction. So the minus here, so the minus here actually gives you the change of sign. And yeah, this is just some test. And then we just produce our Y. So the Y is the sound we are producing. Okay. So these are just some some plotting code. Yeah, how to plot this. So when we sound this, we'll use a function called sound. So make sound, Y is our waveform, and Fs is the sampling rate. Okay, so let's listen to this again. Yeah, I think it sounds like a plugged string, right? It sounds like string, but there's no real string, playing. We're just using the computer and using the simulation to make the sound. And this is the frequency. So the frequency is from 0 to 8,000. So I think this one should be 440, okay, near 440, because this is our fundamental frequency. And this is 2 times 440, right? The integer multiples, and it seems it doesn't have higher amplitudes, higher harmonics. Sorry. Here, so to play with the model, actually we can change this, right? We can change where we plug this. For example, let's say we plug it at the middle. Then how the sound will change. Let's run this. Okay, so here you can see the initial condition changed to the middle of the string, and the harmonic also change here. Okay, so let's skip this second graph for now. Okay, this is a given piano file. Let's just skip this for now. So this is synthesis. Synthesis means the sound we just synthesized. Okay, so the frequency distribution somehow changed, right? The second harmonic is much lower, and let's listen to this. Right. So the sound is somehow darker, but it's probably because we are picking it at this N over 4. Let's change the pickup position. Let's see what's the difference. Okay. Right? It's brighter and louder. It's actually where you listen to this, where you pick the sound also influence. So I don't know, let's see, we pick the sound at N, okay? Let's see, we pick the sound at N, which means we pick the sound at the end, here, the end note. So let's run this. Okay, the initial condition is the same, but let's listen. What's this? Right, so there's no sound because we are picking up at the end position, at the end note. So there's no movement of the end note, therefore it produces no sound. So the pickup position actually changes the perception of sound somehow. Okay, so this is the plucked string, and let's see, we plug it at 7. Because in our example here, right, it's the motion of a string plucked at 1 over 7 of its length. Let's try it 1 over 7 and see how, right, how the sound will look like. Yeah, so this is the distribution of frequency. See the sound. Okay, so it seems it presents more more color or more upper frequencies. Right? Any questions or thoughts so far? Okay, so this is a plucked string, but we also have a struck string. So struck string means let me just maybe run this first, so I can give you an explanation of what is struck string. So for the struck string, the string is still of the length of this, 551 point, but struck string means it's the working principle of piano actually. Like you have a hammer, right? This is your entire string of length L, and now you have a hammer, and you are only producing some very small displacement here, but you are not really not like struck string, a pluck string, right? When you pluck the string, so the string will be deformed like this. But here, so this is plucked, and this is struck. Okay, for a struck string, so think about you have a hammer and you give it a very sharp, right, hit, and then a sharp hit, and then it will have a temporal displacement like this. Okay. So this shape is not necessarily like this. So we can use different functions to simulate the shape of the struck. Okay. So its struck can be a box, can be something like this, right? The box we just saw in the video, or it can be some triangle, right? Some triangle like this, or something like this, you know. So okay, so you can see that here, when we use the struck string of this shape, it produces many, many more harmonics here, right? Let me clear everything. Oh no. So it presents more harmonics here. It's 440, 880, a lot more harmonics, a lot more color. So let's listen to this sound. Yeah, how it sounds like. Yes, much quieter, but it's brighter, right? Maybe let me change this to 3. Change it to 4. Okay, so we change the struck position, and let's listen to the sound. Right. It's about 2. So you can actually play with those parameters and see, different parameter, what's the relationship between the parameter and the sound produced. Yeah, basically no difference. So now we are using the triangle. What if we use the box, the box function? So let me run this. Okay, so you can see here is like a box. Let's listen to this. Yeah, it's similar and brighter. But we can also actually change this parameter here. This is the width of the stroke. Okay. If I run this, you'll understand. Okay, so now it's become much wider. Before that, we have very small stroke, but here it becomes much wider and it influences much more length on the string. And let's listen what the sound will be like. Okay, it's a different kind of color. Oh, it's not a MATLAB library. It's what I wrote. You can see it's homework 5. So it's my first year of PhD. Yeah. So I took the class and yeah, I learned those and I just programmed it myself as homework. I don't know if there will be any built-in library producing those things. But you can see there are not really not many code to do this work. So yeah. Yeah, thanks for the question though. Okay. So what else? Okay. So we tried the box and we try triangle. So now I want to maybe just use another kind of function like sine. Let's see. Yeah. So I want to make it somehow, the shape of a circle like this. And this is the frequencies as here. Did you like realize any difference? I don't know. Yeah. But what about this? Let me change this to 5. And let me start with triangle. And let me generate all those sounds and let's do a comparison. Okay, so this is a triangle initial condition. So this is a change of parameter, right? Let's here hold the triangle. Okay. And we rename as and then we use this as box. Okay, so this is another shape as box. Listen to the sound. Okay. Somehow different. Store this sound. And finally, let's use sine. Okay, so it basically shows you different initial positions, different shape of the struct will produce different colors of sound, right? Because the basic frequency is given already by 440. So only the timbre or the color will be different here. If you can hear the difference. So let's store this sound. Okay. So what I'm going to see now, okay. If you read the paper here, so here is a book called The Science of Musical Sound. Okay, it only talks about the physical models, not really talking about any computer simulation. But when it talks about the physical model, actually it gives us a lot of. Okay, it's a bad idea because let me find this here. Oh, it's a lot of things. Oh no. Okay, here. Because then I can use this to find this, okay, the struct string, the piano. So it talks about the working principle of the piano, right? It's a struct string and blah, blah, blah. And this is the mechanism for the piano, whatever. Yeah, okay, it is here. So it shows us piano is worked as a pluck string and the initial shape is like this. Okay, so it looks like the right, the sine function I just used to simulate this shape. So this is the piano. So this is a working principle of the piano, and this is a struck string. You can see this is a movement of the piano, right? You have a very small stroke of the hammer, and then it induces left traveling and right traveling waves, and this is the wave, how the wave travels on the string of piano. So one thing we want to know is that how well this physical model actually behaves in terms of simulating real instrumental sound, right? So actually in this example, I just downloaded some real piano sound, okay? So this downloaded from some website. It's recorded when a performer plays piano, when the performer press the A4 key of 444 hertz with FF, okay? So let's listen to what this real piano sounds like. Okay, so to sound this thing, this will be piano. Right? So this is the real piano sound. Then what we are doing here is actually that, I found those parameters here. I just did this experiment yesterday. I found those parameters here, and I will use sine wave here. And when I use those parameters, and when I generate my synthesis sound, you can see, right? The piano frequency and the synthesis frequency is somehow they kind of like look like each other. Yeah, except for those upper harmonics. So they kind of like match with one another. And let's listen how well our synthesis works. This is our synthesized sound. This is the real piano sound. Right? So, but the problem is that you need to find a good kind of parameter. Let's see if we change this parameter to 3. Let's listen to this one. Right? So it's somehow like that doesn't really match. And also for different piano, different makings, it also produces different sounds. So if you have 2 pianos, if you press at the same key as A4, they will produce different timbres, okay, because of the physical structure of the instrument itself. So very interesting. When I've used those kind of parameters, it produced kind of like, I would say, very, very similar sound as the real piano, very realistic. Okay, so when we use different initial conditions, also, if we use the box, this is sound. If we use triangle, right? So if we use a sign, oh, I didn't store. Oh, okay. So this should be this one. Right. So it's also have different colors. And finally, if we sound the piano, right? So this is the simulation. So I don't know how much you feel it's like, it's kind of like a very kind of amazing that you can use a simple, very simple computer program, to simulate a real sound, because for piano, right, it's very expensive. If you buy a piano, or if you play the physical piano, it's very expensive to build a piano and make the sound. But now only use the computer and only use a few lines of code, you can simulate basically any. Actually, piano sound is difficult somehow, but for other trumpet or brass or string, they have different methods, but are much easier, different methods. Not really much easier, but yeah, not that complicated actually, comparing to if you buy a real instrument or build an instrument from scratch. So this is what I want to show you, the effect, right, of the physical modeling and simulation, and we just covered in our lecture of the stream model, or the one-dimensional digital waveguide. So now I want to talk about voice synthesis. I think most of you might be more interested in voice synthesis because we are talking every day. And this is also interesting, because you think how we make voice is very complicated, right? We make I, O, U. So how do people make those different sounds? And if it's ever possible for the computer, right, to simulate those pronunciations using physical modeling. So before talking about this, I want to continue with these slides and talking a little bit about wave impedance. So wave impedance, it's not like that's, so there are some physical terms. Okay, we're not going to talk about this, but here, so this is important. So what is impedance? So when two different medium, they meet each other, okay, maybe they of different density, different mass, different quality. When the two medium meet each other at the boundary here, right, it will produce some impedance. So for example, before we talked about the stream model, at the end, at the fixed end or free end, this boundary is like a fixed boundary, right? So this boundary will work like a fixed boundary here, and no wave will be transmitted through this boundary. In the stream model, it will only be reflected back. Okay, so the wave they hit the wall or they hit node, and they will be reflected back because this is closed the boundary, and no wave will be transmitted. But in our real life, for example, here is air. So this is the air, this is water, right? There are two different medium, and when a sound transmitting or propagating in the air, when it meets the boundary and it's going into the water, what's the physical process would be is that actually part of the wave will be reflected, okay, but part of them will be transmitted. So this is the graph that's showing that two different medium, when they meet each other, what's the kind of interaction they have in terms of sound transmission. So these boundary conditions actually is given. Let me see. the boundary, okay, so it says here, okay, so the boundary condition at the junction would be the pressure and the velocity, okay, at the junction must be equal. So this is the where the equation comes from, right? So the two different medium, when they meet at this boundary, the pressure at the left side and right side and the velocity, left side, right side will be equal. And this gives us all those following formulas, how to compute the pressure, and this is the impedance, Z is the impedance, and compute blah blah blah, and also velocity, because the velocity would be the same, and this is where the equality comes from. So we're not going into those details. I'm not very familiar with this also, actually. It's a lot of computation. If you do physics, yeah, you should probably have know this. But finally, you can compute something called the reflection coefficient. Okay, reflection coefficient described by the impedance of the medium. So impedance is a property of the medium, like the velocity. Okay, like the speed of traveling. So this is a property of the medium. So Z2 and Z1, they are of the different impedance of the two medium. And you can calculate the reflection coefficient. The reflection coefficient is calculated as this. Okay, so so the physics here doesn't matter, but the intuition, okay, the intuition here is given by this graph, and this equation is derived by this condition, okay, equality here. So what about the vocal tract? So now we're talking about vocal tract, right? So thinking about your vocal tract here. So from the base is the glottals, okay, glottis. All the way, so it's a tube, right? It's basically a tube. So the filled with air, and this is your mouth. Okay, so you use your mouth to speak, whatever, and this is a tube. But the problem is that this tube model is not like the previous one, like when we talk about the instruments, right? Because the instruments, the tube is of even quality, is even, and it doesn't have the small changes. I mean the nuances there. But for your vocal tract, because you can also because the boundary here, the vocal tract is not fixed. Okay, it's very flexible, and you can give pressure to your vocal tract. And when you give different pressures, it will produce different sound or different syllables, like E, O, A, U. This basically because you are giving different pressures to your vocal tract, and also, of course, it depends on the filter of your mouth, right? How you use your mouth, how you use your teeth is also influence the sound you produce. So the sound you produce is actually determined by the shape of the vocal tract and the shape of your mouth, right? But the problem is that how do we simulate this kind of structure? So it's impossible to use one tube, right, to do this, like what we just did, like this, or we say, okay, open like this. This is too easy for our vocal tract. So for vocal tract, actually what we do is that we divide this to very, very small sections. And actually every section have different shapes, okay? Because when you are applying pressure at different positions along the vocal tract, okay, here and here and there, and then you will produce different shape of your vocal tract. And then when we divide this to very, very small pieces, at every small section, we can see they are, so, okay, this very small section, we can see this is a given tube, okay? This is a fixed tube. There's no change of air pressure or of the medium. And when it comes to the next section, next small section, so within the section, everything will be constant, but the difference will happen at the boundary, right? At the section, like what this graph shows. At the boundary or the junction of the vocal sections, there will be some different impedance, okay? And the impedance will give you different reflection coefficients. And this is where the computation comes in. And after we concatenate all those small sections together, okay, and then we actually simulated our vocal tract, and at the mouth, we will produce the sound, okay? So at the mouth, there is another filter of different shape, but it will, we'll filter this with a proper filter. It will produce the sound, okay? Of this. So yeah, so actually there is a paper on this. Yeah, we're not going to look into the paper, but yeah, I think the graphs here will be more like relevant. So you can see the vocal tract, divided into different sections. So this model is actually called the piecewise cylindrical vocal tract model. Okay, piecewise cylindrical model. Cylindrical means your vocal tract is like a tube. Right. So this at the injunction, there will be different impedance, right? Z1, and this impedance will give you the coefficients, reflection coefficients, and then you can compute the change of sound here. And this is another one, like when you take a small section out, and this is the right. So you still have it's the same as the digital waveguide we just saw or we just used in the stream model. You still have two delay lines, and this one is the right traveling wave, this one is the left traveling wave. And when you get to the mouth, you just add them together, okay? Just add them together. And the right traveling wave and the left traveling wave will be reflected at the boundary. They will be, part of them will be reflected back, part of them will be transmitted to the next section. Okay. And here, when it's reflected, there will be some filter, give it proper like damping or change of sound, etc. And when you concatenate all those sections together like this, and you are basically simulating your vocal tract. So this is the principle of that. I hope it's clear. Yeah, it should make sense, right? Intuitively, at least, I guess. Okay. So now let's see how it works. So this is actually a work that I did like 4 years ago, I guess. Okay, this is much better. So actually, this is called glottal source model. So this is the pulse, the glottal pulse that's produced from your by your glottis. So this is at the right, the base of your vocal tract, and then this pulse will be transmitted through your vocal tract and into your mouth, and you will produce sound. So this is the source of the sound, and these are the text files are the parameters, the reflection coefficients, right? The impedance we just talked about, how the different sections are connected. So they are described by those different coefficients, and these things are actually measured using some sort of equipment. And then the measured number is stored in this file, and we just use this file as the as known coefficients of the vocal tract. And this is the formula. This is the formula of this function. Okay, so because we need to draw this function using the computer. Okay, and you can see there are some calculus thing here, and when you use the function fitting, it uses the Newton's second. No, it's the Newton's iteration. Yes, some numerical method doesn't really matter what it is. But using this function fitting, we can basically get the same shape here, right? The same shape as the glottal pulses. Okay, right? So it's the same shape as before, as we draw. This is glottal pulse, this is derivative glottal pulse, right? It's the same shape as this one. Because they are determined by those parameters, and when we determine those parameters like TP, TE, TC, TO here, and we just, it's just a bit basic function fitting. Okay, it's not important part here so far. And now we are going to concatenate those different pulses. So we can use different kind of functions here. Let's say we try this one with exponential up. So there are different kind of functions we can choose from. And after that, you can see this is the glottal pulse. Okay. And this is glottal pulse that's produced by your glottis. And we can play the glottal pulse. Right? So this is what's produced as the source of that. Okay, let me probably draw this again. Okay, so this is the vocal tract. This is your mouth. And the glottal pulse is what we produce here. Okay, we produce as the basic, the fundamental material is like this. Okay, so this is what your glottal produces here. And then the next step is that we'll use the coefficients and make it going through this vocal tract and your mouth, and let's see what kind of sound it will produce. Okay. So this is the glottal. And now we can choose some vowel. Let's say we choose R sound. Okay. So here is the waveform. Let's play. Right? So listen to this source again. Right. Okay. So maybe we can do some other experiment. Exponential. Okay. So I remember. Let's choose another vowel. Maybe a bird. Right. Maybe another one, E. Right. So the source is the same. The source is the same. The source is like this. By using the same source and using different, physical modeling of the coefficients, and we can produce different vowel sounds here. Right. So ooh, food, ooh. See this. Okay, so this is what we just generated. It's somehow like, yeah, I think it works okay, right? At least you can distinguish that this is it is some vowel sound that's probably produced by human. Okay, so to make it more realistic, I choose to add some Gaussian noise there. Okay, so to add some Gaussian noise, which basically means let's say we choose this one, this function. and add Gaussian noise. So Gaussian noise is something like this. So before that, before adding the Gaussian noise, the function is perfect. Okay, the glottal is perfect and it's smooth. But actually, when we just talk, or when our real glottal cannot produce something this perfect, okay, this smooth. So it's always some noise, some random things in the glottal in the glottal pulse like this. So I just add some Gaussian noise to make some fraction, maybe add some realness into the simulation. So let's play the source. So here I changed the function. Okay, so before that this is down, right? Ah, ooh, so ooh. So you can change the function here, but whatever. Let's try some other vowel. Okay, so you can see this is the waveform of the vowel sound, and this is the spectrogram. Okay, so in the spectrogram you can see some of the formant, some formant. Okay. Ooh, right? Okay. So the reason is that it's different kind of direction, because actually I use different function here. When I use exponential down, it produces that raise up. When I use exponential up, it produce something down. So let me still use this exponential down, but let me change to some other vowels like this. Right? It sounds somehow like a real human talking, I guess. Let me see. Maybe this one. Oh. Okay, let me play everything we just generated. Right, you can hear the sound when we add some Gaussian noise. It's somehow like maybe more realistic, because the kind of the friction or the noise, the imperfection is captured in the model. Yeah, when I plot this everything out, looks like this. And you can see different vowel is of different shapes in the spectrogram, right? This is something called formant. Okay. So let me clear storage. Any thoughts of this? Or if you have anything, do you want to try something out? It's also okay. Okay, so maybe let me try some other function. Okay, so random always generates something not very good. So constant, let's see, constant is the most unrealistic sound. Okay, so this is a constant. Okay. Okay, so as you can see, everything is just flat, because we are using the constant function to simulate the glottal source. Yeah, all is the flat. There's no tune, no up or down there. But let's see, if we change it to exponential up, it will produce something else. Okay. Seems ooh. Right? So whatever, I guess I hope this can give you some inspiration in terms of physical modeling. And if you're interested, I can share the files with you if you want to experiment. And also using MATLAB. Actually, this thing also, although this work looks like a lot of things, actually, you can see there's many many code, looks complicated, but actually no. Actually, the core of this work is only on about the voice synthesis. Okay, and for voice synthesis, it only requires very small portion of code. No, only a few lines of code like this. And once you have the coefficients here, so K, okay, so S is loaded from those texts. Okay, so what? So in the text file, there it encodes some some of those numbers, and those numbers are actually this something like that, like okay, those numbers are actually reflection coefficients. Okay, this is P computed by the impedance. And once you have this file, and you just input this into the model, and you just use a digital waveguide we just talked about, right? The two delay lines modeling two traveling waves, left and right, and apply some filter. So only this part, and then you can just simulate basically all kind of sounds that your vocal tract could produce. So